Okay, off we go. So yeah, don't forget about the attendance quiz. So the quiz disappears in a minute and a half. Right there's the code. Make sure to enter it. Make sure to check and confirm that your score records. Make sure that you get the credit. You got to see where it says like 1 out of 1 or something like that, right? Make sure you get the actual credit and that it's recorded. It disappears in about a minute now. Okay, so back into the math. Welcome back, everyone. Let's see, where am I? Yeah, okay. So, continue on with graphs and level sets. We were talking about graphs and level sets last time. We saw one relationship between them. The big point to keep in mind is they are different, right? They're completely different constructions. And we saw, though, that they're related because level sets are just horizontal cross-sections of graphs in some reasonable sense. Here's another relationship kind of between them. And that is this algebra right here, this trivial little nothing, barely happened, right? I mean, I took the right side and subtracted it to the left. No big deal. Shows that if you start with a graph, you can easily rewrite it as a level set. That's fabulous. Right? Now the reason we care about this, sometimes we're given a graph, or someone says, "Hey, let's study the graph of this function, whatever function." And the thing that they want to know about that graph, it's something that I could get to with the calculus of level sets. Now I know we don't know what that is yet, but we'll be getting to that very soon. Man, I sure wish I could use the calculus of level sets on this problem. Okay, well, whatever it was that came to you as a graph, just pull this little fast one. Now it's a level set. Now you can use the calculus of level sets. Right? It's a real cool little slick move. Now the sticky little detail is, of course, this function is not the same as this function. Right? So the function whose graph you were talking about, it is a level set, but it's a level set of a different function. Everybody see what's happening there, right? That's clearly a different function. This is just f. This is y minus f. Not the same. Now, really easy to mess this up, right? And because look how easy the algebra is. It almost feels like nothing happened. And if it feels like nothing happened, then it might feel like, and therefore the functions are the same. But they are importantly different, as you can see. And that will affect your answers very, very strongly. Okay, let's see a quick example of this in action. Now again, we don't really know the calculus of level sets yet, but suppose someone gives you this function and asks you about the graph of that function, and you want to know some information about the graph of this function. By the way, we've already seen the graph of this function, right? AKA, we've seen this equation before in a couple of different contexts. Today, by the way, we're going to talk about how to figure out what this actually looks like. Anyway, if you want to understand something about that graph, and if you would like to use the calculus of level sets, don't apply the calculus of level sets to f. That's a bunch of nonsense. We're not interested in level sets of f. We're interested in the graph of f. If you want to apply the calculus of level sets, you got to rewrite it, pulling this little fast one, same exact little fast one of algebra. Now it's rewritten as a level set, and now you can see what function it is. This function down here, g, this is the function to which you would apply the calculus of level sets. Whatever that, aspect of that might be that you're interested in. You apply the calculus of level sets to g, and that will tell you information about the graph of f. Everybody happy? So it's a real nice trick, but it comes with, it's delicate. Right? It's easy, it's fast, it's delicate. If you're not careful, again, your bridge falls down. Okay, now the bad news, I get, the disappointment here is that this is, oh, sorry, you had a question.
Why look at use the calculus of level sets?
Yeah, well,
why is it useful?
Yeah, I'll be able to tell you once we know some calculus of level sets. At the moment, we just don't know any. But there are some derivative constructions that we can write down that have very natural geometric properties, and that will allow us to answer some neat questions. And so we'll just have to wait till we get there. Yeah. Right. Okay, yeah, so the disappointment here is that this is a one-way result. Every graph is easily rewritten at the level set, not vice versa. Not every level set is a graph. Here's an easy counterexample. Here we see a level set. That's a level set. Is this equation... Is this equation the graph of some function? Let's see, if it was a graph, I'd have to be able to rewrite it as either y equals function of x or x equals function of y, and you can't do that. And I know what you're thinking. I can write y equals plus or minus the square root of blah blah. Plus or minus is not acceptable when you're writing a function. Functions are only allowed to have one output value given your inputs. Does that make sense? Okay. So, one-way result, oh well. All right. Okay, so the next several pages is going to be about some tools for your toolbox concerning multivariable equations. So we've seen a couple of examples of how multivariable equations are going to come up. If you want to look at a graph of a function, you get a multivariable equation. If you want to talk about the level sets of a function of, let's say, 3 variables, you get another multivariable equation. You get equations of 3 variables. We don't know how to draw the solution sets to equations of 3 variables. So I'm going to give you a couple of tools. Here's the first one. It's a real nice little result. The condition is this really easily observed condition I have here in green, and that is just look at where your x's and y's show up in your algebra. And if your x's and y's always are part of this expression, it's easy to, again, you just look and see, right? If every x and y is part of this expression, easily checked, and the powerful result we get is that your surface is rotationally symmetric around the z-axis. So that's a big, powerful geometric conclusion for the low, low price of casual inspection, and just make sure x's and y's look like that. Okay, talk about why this is true. All right, there are a couple different ways to see this, but let's do it like this first. Let's suppose we have some point. We're looking at one of these equations as described. Got a point there. Now I'm going to say, let's take that point, and I want to rotate that point around the z-axis. That's just a geometric move, right? So I'm going to rotate around the z-axis, and let's consider in particular one of the points that I get as I rotate the original point around the z-axis. Now I've got 2 points. Is everybody with me so far? These are different points, different coordinates. If you plug them into an equation, you're plugging in different numbers. You would expect different results. Here's the thing, though. If your equation has x and y only in this form, notice that is literally the distance to the z-axis, otherwise known as r, in cylindrical coordinates. And these 2 points, they have different x's and they have different y's, but they have the same r because I produced the one from the other literally by rotating, which doesn't change the r. So these 2 points have the same r. Also, another nice thing about rotating around the z-axis, doesn't change the z-coordinate. So they have the same z. Now, if you think about it, your equation, yeah, sure, it's got x's and y's in it, but the x's and y's are all part of an expression on which those 2 points already agree. And yeah, they have a z-coordinate, but they have the same z-coordinate. So as far as the algebra of this equation is concerned, these points behave. When you plug those numbers in, the arithmetic's morally the same arithmetic. And so they will either both be on your surface or they will neither be on your surface. That make sense? So, nice punchline. Right? So if we have this feature that no matter what point you look at, as you rotate it around, it's either, if it was on the surface, it stays on the surface. If it wasn't on the surface, it stays off of the surface. The only way a surface can do that is if it's rotationally symmetric. So, really nice punchline. Now, why do I care? How am I going to capitalize on knowing that my surface is rotationally symmetric? There's a really cool trick that allows us to capitalize on this. Here it is. If your surface has this symmetry, you can look at any cross-section in any plane containing the axis, any plane, whatever, and then just rotate that cross-section and it'll produce the entire surface. Now that's a geometric appeal, right? You got to think about what does a rotationally symmetric surface look like, and because it's rotational, think about any plane as you rotate it around, it's just going to trace out the entire surface. Is that reasonable? I hope. Okay. All right, let's see it in action. And here's our familiar equation. Again, I've been making reference to this equation several times in the past. I asked you to trust me that it's kind of a bowl, right? And here's where we're going to see how we know that's true. Okay, observation number 1. X and Y appear only in the special form. Now, let me address a quick complaint. You might say, hey, that doesn't look right to me. Where's the square root? Okay, well, I can rewrite it as square root of x squared plus y squared squared. So x and y appear only in the special form. Is that cool? Everybody happy? All right, so that means that it is rotationally symmetric around the z-axis. I like to highlight the z-axis in there just because a reminder of, okay, everything that I know is about this surface, I can just rotate around and I'm still in business. Let's pick a cross-section. By the way, suit yourself. Any cross-section is fine. I'm going to use this one. But if you wanted, you could use that one. And if you just want to make your life pointlessly difficult, you could also use one at some sort of an angle, right? Make it, again, pointlessly difficult. I don't encourage that. So let's go with what we already have planned here. So I'm going to pick that plane right there. Contains the z-axis. It has to contain the z-axis. And let's see what happens. Well, you take that, you plug it in, the equation turns into this, and that I understand. Right, z equals y squared, nothing to it. It's our old friend, it's a parabola, easy. I can do better than that. There we go. I claim it's all over with the shouting now. I know that my surface is rotationally symmetric. Now, if it's rotationally symmetric, that again, very few surfaces are. How many surfaces can you think of that are rotationally symmetric around the z-axis and where one of the cross-sections is like this? There's really only one thing. You just literally take this cross-section, rotate the cross-section around the z-axis, and it produces what this surface kind of has to be, which is what I had claimed. It's kind of a bowl. You buy it? Okay, so this is a real neat trick, very powerful. Big fan. Let's see, I guess I can. Actually, I don't know why I'm erasing. It's sort of this habit. I'm just going to leave all that there. Let's see another example. There we go. And we've got an equation there. Again, I don't immediately recognize what this is. What are we going to do about this? Well, notice x and y appear only in the special form, so this is rotationally symmetric around the z-axis. Still don't know what it looks like, but I know it's got that symmetry. Okay, cool. Pick your favorite plane containing the z-axis. Now, I previously picked the yz plane just to show you we can do it the other way. Let's pick the xz plane. Doesn't matter. That plane is y equals 0. I can plug that in. Let's see what the equation turns into. It turns into this. Again, flashbacks to high school, right? We recognize that. That's a hyperbola. That's a hyperbola that goes like this. By the way, if high school was a long time ago and the high school algebra, and you remember that, the hyperbola, it could go this way or it could go that way, and how do you remember which way it goes? And if you find that a little confusing, if you can't quite remember, come talk to me in office hours. I'll show you that there's a couple of real easy little tricks that allow you to get that right every time. And you want to make sure that you know some reasonable trick. Please don't try to memorize your way out of that problem. It's not a good strategy. You will forget eventually. So anyway, come talk to me. I'm happy to show you my tricks. Okay, so again, it's all over with the shouting. We know it's rotationally symmetric. I know this is one of the cross sections, and now I just have to think, well, what do I create when I rotate that around the z-axis, and I claim I get something kind of like that. And it's a rotation of a hyperbola, so we call it a hyperboloid. Everybody okay? I mean, it's all good? It's the end of a long week, maybe? Okay. All right. Now, what if I have something like this? And here's the bad news. X and Y do not appear only in the special form. There's a minus sign there, and I can't sort of do clever algebraic equivalences to make that go away. It's just not going to work. So this is not rotationally symmetric around the z-axis. It's really not. Okay, now that said, if you think about it, what was so special about the fact that I picked X and Y to be in the special form and Z to be the axis of rotation? Was there something intrinsic to the geometry? Is Z, X, and Y, are they intrinsically different in some way that makes it only work that one way? No, not at all. So you can make highly analogous arguments to produce two more highly analogous sort of symmetry theorems. And I think those are really good exercises. I want to encourage everybody to take a crack at them, right? It's going to be a lot like this. Just think about how this special form, if it were X and Z, what distance to what axis would that be? Then you make an analogous argument accordingly, and everything will work out just fine. Okay, so let's apply our analogous theorems. Even though X and Y don't work, Y and Z do. Is that cool? So that means this is rotationally symmetric around the x-axis. Oh, come on. I've got to get better at my drawing. There we go. So, yeah, okay, great. Now, again, I get to pick any plane I like. Any plane at all. It's got to contain the axis. Take your pick, your favorite plane containing the x-axis. Not that it matters, but I'm going to pick the xy plane here, which is described by z equals 0, which I can plug in. The equation then becomes this. Again, flashbacks to high school algebra 2 or whatever, and hyperbola like so. Make sure you get it the correct sort of direction. If you have the direction wrong, you'll get wrong answers, etc. So you got to, again, think through that old algebra, and again, come talk to me if you're not sure how that should work. And again, it's all over but the shouting. So my surface is rotationally symmetric around the x-axis. What do I get when I rotate this orange curve around the x-axis? And, well, I get something that looks kind of like that. And it's a hard one to draw. And that's a terrible picture, and I'm not happy with it. But that's the best I know how to do. And by the way, there's a lesson to be seen there. Don't set the bar too high when it comes to drawing stuff. Computer-generated figures they have an unfair advantage over us, right? We can't hit the marks that they can produce. The goal is not perfection. The goal is to be able to draw something well enough that you can kind of make some sense out of. Okay, I sort of see what that thing looks like. Is that cool? Everybody's happy? Yeah.
When you say you can do like a rotation around every axis, is that just because you can always convert one of them into like a cylindrical coordinate? That is.
Yeah, I mean, kind of. I mean, let me just point out this cylindrical coordinates argument that I made here was sort of an alternative argument, and it's convenient because we've already done it. And I'm a big fan, as are all mathematicians, of reducing a problem to a previously solved problem. Absolutely. But notice we don't need that cylindrical argument, right? You can make this argument that I did up here. This makes no reference to cylindrical coordinates, right? And this up here is much easier to adapt. If you say, I would like to invent 2 more coordinate systems, then, I mean, I hear where you're coming from, and, I mean, I buy it, but it's not mathematically valid until you actually flesh out exactly what do you mean by these 2 new coordinate systems you're describing, and what are the conversion formulas, and I think it'd be a lot more work. Yeah. Does that make sense?
But we already know this cylindrical coordinate, right?
Yeah, you already know. Yeah, that's right. For going around the z-axis, the existing cylindrical coordinate system is perfect, and it's just kind of a lucky break. Yeah, absolutely.
I mean, the fact that we have it arranged in x squared plus y squared is pretty lucky too. So.
Yeah. Well, that was no coincidence. I did that on purpose. Yeah. Absolutely. Okay. All right, moving along. Okay, so here's the next little trick, now, tool for your toolbox, right? This is a little weird. The premise of this is that I already have an equation for which I know what the set of solutions looks like. Now, in the starter example, this equation right here, yeah, I do know what that looks like. I mean, I can convert this to spherical coordinates. This is just rho squared equals 13 squared, so rho equals 13. It's a sphere of radius 13, nothing to it. You could make a rotation argument, right? X and Y appear only in the special form. So, another way to go. Okay, here's the question. The weird question I want to ask. If, weirdly, I were to say, hey, you know what? Everywhere I have a z, I would like to replace that z with 2z. I'm going to get a different equation. That's a weird thing to want to do, but let's just play the game, so play along with me. If I tweak my algebra like this, how will that tweak the solutions accordingly? Right? If you change the algebra, you change the geometry. How does this algebraic change cause? What is the corresponding geometric change? Okay, so that's the question I want to ask. And, well, let's think it through. I have here, for example, there's a point 3, 4, 12 that you can confirm works in that original equation. It's just arithmetic. It's kind of fun arithmetic, by the way. It's that's what do they call it? A Pythagorean quadruple. Right, like 3, 4, 5 is Pythagorean triple. This is the Pythagorean quadruple. I like easy numbers. Is that point going to work in this equation? No, of course not. Nonsense. Different point. Different equation. Everything's going to be different. It just doesn't work. here's the clever move. I can think about this point, 3, 4, 6, and that does work. And let's just think through why, right? The problem with putting this point into this new equation is the 2. That takes this 12 that I wanted to square, and everything works, and it turns that 12 into 24, which is totally different and, again, crashes and burns. So the clever sort of smart alecky move is to say, okay, let's divide the z-coordinate by 2. Then when my tweaked algebra multiplies it by 2, I'll have the 12 that I had in the first place and everything works. Everybody see what I did there? I mean, so it's a little smart alecky, but whatever point you give me on the sphere, I can play this game and produce a new point that will solve the new equation. So I have kind of a one-to-one correspondence between points on the old surface and points on the new surface, and the way those relate to each other is I just divided the z-coordinate by 2. Said differently, this surface is what you get when you take the old surface and you squish it by a factor of 2. And this is a really nice conclusion, right? So real simple algebraic move, nice little pithy little geometric consequence. Everybody on board? Okay. So let's see. Let me clean up the mess. So yeah, this algebraic move causes this geometric consequence. Now, how to think about this, and by the way, how often are we going to be precisely exactly replacing z with 2z? Not so often. It's not the point. The point here is that the geometric consequence is sort of the result of kind of doing the opposite to the z coordinate in anticipation of countering the sort of, what we did algebraically, sort of multiplying by 2 up here. So I divide the z coordinates by 2 in anticipation of having to multiply them by 2. Right? So in some sense, all you have to do is just undo whatever the algebra did, and that'll be your geometric consequence. So for example, let's suppose that instead of what I did here, let's suppose everywhere I had a z, I replace it with z plus 3. Well, you probably see this coming, but what I would do is I would take all the points on this sphere and I would subtract 3 from their z coordinates, because by subtracting 3 from those z coordinates, and then when I add the 3 back in, now it all works again. So there's a punchline, which is this right here. Whatever, in some sense, you do to a variable in an equation, the opposite happens to the surface. And I'm deliberately stating this kind of intuitively. I don't want to make this. I'd have to write down several different theorems if I wanted to make this formal, right? But the intuition, I think, is good enough. Just think in terms of undoing what you did to the algebra, and that's how it tends to work. So here's a nice example. Let's try to make sense out of this equation. How would I understand the set of solutions to that equation? And the first answer I have to give is I don't know. Then I can say, well, I wonder if I could make a rotational symmetry argument. No. The A, B, C in the denominator, presumably different numbers. I'm not going to be able to get rid of those because they're different. And so X and Y, Y and Z, none of them appear strictly in the special form, and there's nothing you can do to the algebra to make them show up in the special form. So there is no rotational symmetry argument to be made. So what I do is I think back to this, which I know what that looks like. That's easy. And then I ask, okay, what did I do here? What were the sort of algebraic moves? Well, I replaced x with x over a. Algebraically, that's what I did. So geometrically, what undoes that? What undoes dividing by a? The answer is multiplying by a. And so the effect of that is to stretch the surface in the x direction by a factor of a. Is that cool? Everybody on board? And you can probably see the rest of this coming. I replace y with y over b, and that's going to stretch in the y direction by a factor of b, and likewise for z. So, is everybody good with the details so far? Okay, so here's the sort of strategic summary. The strategic summary is that if you start with an equation like this, look at something simpler that you can relate it to. Think about what that looks like, and then do the corresponding geometry to conclude what you actually want. Sort of a 3-step process there. Does that make sense? All right. Okay, there's a little landmine here I want to make sure everybody sees. This is easy to mess up. I've seen a lot of students mess this up. I ask, what does this thing look like? And then I think to myself, hey, I know what that is. That's a paraboloid. That's easy. And then you'd think all I have to do is figure out the stretching argument or the stretching factor. And doesn't it look like my x has been replaced by x over a squared? Typographically, it kind of looks like that, right? That's not how it works. Let me write this out a little bit differently. I'm going to rewrite that term over here as x over a quantity squared. And the point is, the squaring happens to x, and so the squaring also happens to whatever you replace x with. So the question isn't just, don't just look at the characters on the page, right? You got to think about what do the characters mean. The fact that we have a square of the x, whatever I replace the x with, that whole thing is going to have to get squared. So it's only x over a that I want to square, given what my actual goal is. Everybody see the landmine? It's really easy to mess this up. I mean, I'd say a third of the papers that I used to see, right, before I started making a big deal out of this, would get this wrong. So I'd like to cut that number down to, 0, of course, but let's get it down as low as we can. This is why, this is where that landmine is, and now you just have to make sure not to step on it. Everybody happy? All right. Okay, so there's you can think through the details of these remaining examples. The book has a few other examples. I encourage you to take a look at those. Again, the book's a good book. I like the book, and make sure to be reading it. Okay, so we're done with 2.1. Real quick, let me talk about 2.2. 2.2 we're going to skip. Right? You can see we're moving on to 2.3. The reason we're skipping 2.2 is tough choices kind of a deal. This one, again, it just doesn't fit in very well with the course. 2.2 is about limits. It's mathematically very important in a math major kind of rigor sense of the word, right? And when it comes to developing geometric intuition and solving problems and let's get stuff done. From an engineering standpoint, most y'all are engineers, I know. It's not that important. So it makes me a little sad because I'm a mathematician. I would love to sit around and I would love to spend a week talking about 2.2, and we can't. And Oh well. So anyway, y'all are not responsible for 2.2. So moving along to 2.3. I should say a couple of places here and there, I will make some references to, to make this precise, we'd need to talk about 2.2. In those cases, you don't need to worry about. I'm just going to mention it in case somebody's uncomfortable with maybe me, pulling a fast one, right? But it's not going to be anything y'all need to worry about. Okay, so multivariable derivatives. Turns out there's several of them. There's like 4 or 5 of them. 6 or 7, depending on how you count. Which is weird, right? Y'all have seen derivatives in single variable calculus, and in calculus there is just the one derivative. Derivative means one thing in single variable calculus. It's going to mean several things in this class. So, get ready for that, right? You're going to have to think about different kinds of derivatives, which brings up the question, if they're different, why do we use the same name to talk about them? And the answer is that the various different kinds of derivatives we're going to talk about, they all have this unifying feature. All of them have this feature that in some way or another, they relate input changes to output changes, right? If you have a number that goes in and a number that comes out, if you fiddle with that input number, if you change that input number a little bit, well, you're going to change the output number a little bit. And the question is, how do you relate how you change the input to how you change the output? Okay, so as we go through and talk about different derivatives, be on the lookout for, wait a second, how does this relate input changes to output changes? Okay. We're going to start with partial derivatives. Mostly because the book does. If it was 100% up to me, I would not start with partial derivatives. I think there's a downside to starting with partial derivatives. The downside is this warning right here. When you leave this class, I really, really hope that you do not leave this class under the delusion that partial derivatives are the most fundamental point of view on derivatives. I don't think they are. I think they're a fabulous tool. You can't do business without them. Absolutely. But ultimately, I think you should be thinking about derivatives in a different way. Starting with something that isn't really the best point of view leaves the risk that you'll hang your hat in the wrong concept, right? And so anyway, you've been warned. We are going to start with partial derivatives. Good news, they are easy. They're really easy to write down. They're really easy to compute with. They're really easy to kind of get satisfaction from because they look a lot like single variable derivatives. That's why most books do start with partial derivatives. But again, don't hang your hat. Okay. Here's the definition. A little bit of a wishful thinking in this definition. We have a multivariable function. We have several input variables. We're just going to say, you know what? Let's pretend most of them are constants. It's wishful thinking. Can you really do that? It seems like cheating, right? I mean, most of the time in the real world, none of your variables are going to be actually constants. Right? So this is some very hypothetical, wishful thinking, kind of very suspicious, frankly. You should be a little bit concerned that this might be nonsense. Right? I would encourage you to be suspicious that this might be nonsense. That said, we're going to hold most of them constant. We're going to leave one as a variable. That means I have a single variable function. Right? I had several variables, and then what had been variables, most of them were no longer variables, and now I have one variable, so single variable function. And then just take the derivative. Good old-fashioned single variable derivative. All right? That's all a partial derivative is. We'll do several examples in a moment. Let's talk about the notation, though. This is the most common notation. Do be careful, that symbol right there is not a D. You can't write it as a D. It would mean something that is not what you mean. And it's just not acceptable. Right, so please got to be careful about that. I know it seems silly, but it does matter. Take some time and get comfortable with writing this little symbol. I know there's probably several instances in this course where you're going to humiliating process like you're in third grade again, but you got to actually practice how to make these new little characters. What I did, and I encourage you to do the same, is to just dedicate 3 minutes and a piece of paper and write, just practice, and the first few that you're going to find don't look very nice, and just think about it and practice and improve on it, and eventually you'll be able to do it comfortably and proficiently. And again, kind of a humiliating process, but everybody has to do it. Okay, also, very importantly, it's not the lowercase Greek letter delta, and again, that's not an acceptable substitute, so don't do that either. Alrighty. Now, another notation that does get used is this right here. There are some very nice advantages to this. Pros and cons. It vaguely kind of like Newton's notation for derivative, right? The prime, f prime, in that it is not writing it as a fraction. And in some ways, partial derivatives behave like fractions. And in some ways, not only do they not behave like fractions, but you will get importantly wrong answers if you treat them as fractions. So I think there is actually something a little bit unsettling about that notation. It's bad in some ways. You can use it. Obviously, you can use it. I use it all the time. I encourage it, blah, blah, blah. But don't get too casual and comfortable in thinking that you can just deal with this as if it's a fraction. It's really not. Okay, more on that when we get to some nice counterexamples. Let's do one. Let's take the y partial of this function. Looks like a nightmare. Product rule, chain rule. Oh my gosh, right? Looks like super tedious. But keep in mind, since we're doing a y partial, x and z are constants. So that's a constant, which means that's a constant. That's a constant, that's a constant, that means that's a constant. That means this is just a great big constant. And the y partial of y squared is pretty easy, right? I mean, how do you take the derivative of y squared with respect to y? Well, it's 2y. And the constants do what constants do. Multiplicative constants come along for the ride. Done. Everybody see how that worked? Really easy. Super. World's easiest derivatives to compute. All right. A couple more examples real quick. Let's see here. Let's take the partial with respect to x of this thing. Well, wait a second. If x is my variable, that means that y is a constant, which means this whole exponent is a constant. And when you have a function to the power of a constant, then you just do the power rule thing. And don't forget the chain rule. And it feels wrong as you write that down, right? It feels really uncomfortable as you write. Wait a second, isn't that a variable? I don't think we're allowed to do that. Isn't this like an exponential or something? Nope, constant. Everybody okay with that? Okay. And then likewise, let's see here. Let's take a partial with respect to z of this thing. And again, constant. So constant. And this is just a straight up exponential. This is k to the power of z. And we have a pat formula for how to take the derivative of an exponential. And of course, the base is this weird other number. x squared plus y squared, so you got to, deal with that. Everybody happy? Cool. All right. Now let's talk about the geometry. Again, I want to remind you, if you look back at the definition here, this is a very uncomfortable definition. It seems like we're cheating. We're playing this make-believe game where we're pretending that things that are variables, or we're pretending they're constants. Seems very suspicious. It seems like this might be nonsense, and you should not just immediately assume that because someone wrote it down that it must be natural in some way. Right? So I need to persuade you that this is actually geometrically natural. So what does this look like? I want to remind you, geometric interpretations depend on whether you're looking at a graph or a level set or what have you. The calculus of graphs is not to be conflated with the calculus of level sets, which is not to be conflated with the calculus of parameterizations. They're all different. Right? So when you say, what does this look like? What are the geometric interpretations? We got to be clear what kind of a picture are we looking at. We're going to start with graphs. You can see right here, we're looking at a graph of a function of two variables here. The graph of a function of two variables, of course, is a surface. So everything we're about to conclude here applies only to graphs. And really nice, let's finish the details. We're computing it at this point. And let's see, we're going to be taking a partial with respect to y. And so now begins the analysis, and what does this look like? How do I, on this picture, how do I visualize the partial derivative with respect to y? I'm just going to take it one step at a time and start drawing pictures of this process itself. Keep in mind the very first thing that we do when we take a partial with respect to y is we fix the other variables. X is our only other input variable. So I'm going to fix x. And keeping in mind that we're starting at the point where x is equal to a, fixing x means that x must stay at the value a, which is just a vertical cross-section, right? So this the first part of this partial derivative calculation. We're just taking a vertical cross-section of our graph. And that cross-section, of course, is this curve. Everybody with me? So the next observation I'll make is that, let's see here, we need to interpret this, how it relates to a new single variable function. We'll check it out. We are looking at height. That cross-section is giving me height as a function of how far I am along in that direction, namely y. This curve, this cross-section of my original multivariable graph is the graph of my new single variable function. This is the graph of my single variable function, function of only y, because height is a function of that variable. And so how do I take the single variable derivative of that graph? Well, the single variable derivative of, how do you interpret single variable derivative on a graph? Well, it is the slope of the tangent line. So the y partial is the slope of the tangent line. Boom. Just like in single variable calculus. Now there's a couple little asterisks. You got to be real careful about this. It's easy to mess this up. Don't forget that this is only of the graph. They don't make a big deal out of this in Calc 1 because in Calc 1 every picture is a graph. They don't need to make a big deal out of it, right? But we do. Don't forget this. It's a slope only if you're looking at a graph. And the second thing you have to remember is there are a lot of different directions in which you could talk about the cross-section and therefore the resulting slope. And we, very importantly, are going in the y direction. And so it is the y, the tangent line in the y direction that we have to be interested in. There's lots of other tangent lines. This is the one that we care about. Okay, last quick thought, super quick. This is how to interpret the partial with respect to y. I want y'all to think through, how would you make sense out of the partial with respect to x? You're going to shamelessly copy from this argument, right? Just set it up the same. Think about what each step of the process means. The pictures are going to look a lot like what we've got, but different, of course. And just think about how that changes. And the nice punchline is it's exactly what you would think it is. But again, it's a nice exercise to think it through. Okay, y'all have a great weekend. See you later.